Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yeah, we're good to go. The last talk of this session will be given by Ece Kamar from Microsoft Research, and the title is Combining Human and Machine Intelligence in Large-Scale Crowdsourcing.
Thank you, and also thank you for the earlier advertisement for the talk. I will be diverging a little bit from the general theme today because this talk is not only talks about machine learning, it really talks about the synergy between using machine learning approaches with decision-making approaches for solving a real-world problem. So I'm a researcher in the adaptive systems group, and in our group what we are working on is developing systems that can function in a stochastically changing world. And these systems need to interact with its environment and with also actors, different actors that exist in this world. So such an adaptive system needs to have a set of capabilities. One of the most important capabilities is making sense of the world through noisy and partial observations about the world. And of course, machine learning approaches are crucial for having this capability. But usually, having this capability is not enough. These systems also need to act effectively in the world. And for having this capability, we need to have good decision-making models as well as these models of the world. And there could be like POMDP-like algorithms, and that's what I will be talking about today. But also, there could be some reinforcement learning algorithms too. And in our group, we are working on a set of domains varying from dialogue systems to assistants that can act in mobile systems to other like office-like assistants for users. But today, the particular domain that I want to talk about is crowdsourcing. And other speakers today have been talking about crowdsourcing, but just as a recap, in the recent years, crowdsourcing has been really popular for providing programmatic access for human intelligence. But the current crowdsourcing applications have one particular drawback, which is it is very difficult to manage the quality in crowdsourcing. The responsibility of managing these crowdsourcing tasks and ensuring quality is on these task owners. For example, as a person going to Mechanical Turk, you need to say, I want to hire 3 workers for this task, I want to pay this much for this, and this is my consensus. This is how I will define my ground truth afterwards. And this is not the best way of doing this because as a task owner going to Mechanical Turk for the first time, you really don't know what are the parameters are the best ones to do. And this is not the best use of people resources, and also at the end of the day, we are not really maximizing our worker resources in the best possible way. So today I want to talk about CrowdSynth, a system that we are designing for managing crowdsourcing tasks. CrowdSynth has 2 main capabilities. The first capability is machine learning capabilities. It has a set of machine learning models for learning about tasks and workers, and also for fusing machine analysis with the noisy worker reports we are getting through crowdsourcing. In addition to this, it has decision-theoretic planning capabilities for optimizing efficiency as we are solving these for these crowdsourcing tasks. CrowdSynth is designed for a special subset of crowdsourcing tasks that we call consensus tasks. In consensus tasks, the task owner has a question in mind. It doesn't know what that correct answer is, what the correct answer of the question is. But it can go to the crowdsourcing system. The crowdsourcing system can hire multiple workers. And the idea is if we can ask sufficiently many people, the consensus of these workers will give us the correct answer of the solution. And in this system, we are paying money or we are spending time with each worker, so hiring each worker is costly. And we see examples of consensus tasks in many crowdsourcing applications, in games with a purpose, in paid crowdsourcing platforms like Mechanical Turk, or in citizen science applications like Galaxy Zoo. However, solving consensus tasks effectively is not trivial. First of all, in addition to having these noisy workers providing us input, we could also have some automated task analysis. For example, we could have a machine learning model in addition to these workers that are providing hypotheses about what the correct answer is. So there's a question about how to fuse these automated analysis with human input to get to the correct answer as cheaply as possible. Also, as some other speakers pointed out today, not all workers or all tasks in these crowdsourcing systems are equal. Some workers are better than others, and some tasks are easier than others. So there's a question about how do we aggregate these people's reports together to get to the answer quickly. And finally, each worker that we hire provides us some evidence, but each worker is costly. So there is a question about, and I think somebody in the audience pointed out this question before, how many of these worker reports are enough? When is it fine to say, I'm done, I'm just hiring this many people, and this is the answer that I want to give to the task owner? So CrowdSynth is designed to address these questions. It has access to some automated machine analysis, but it has also access to workers in a crowdsourcing system. When a consensus task comes into the CrowdSynth system, it can decide to hire workers, and in return, it gets a worker report. And at each step of this process, it needs to make a decision between hiring an additional worker and paying more money versus stopping, getting a prediction for the correct answer and giving it to the task owner. And CrowdSynth has multiple components in it. It has task and worker databases that stores historical information about the tasks, what their correct answers, what their consensus answers has been, and what workers had set for these different tasks. And then it has a future generation component that gets the automated task analysis, the sequence of worker reports collected for the task, historical information coming from the databases, and generates a set of features describing the current state of a consensus task. In addition to these features, now we need to have some predictive models for making sense of these features. So we have two particular models, answer models, for predicting the correct answer of a consensus task at any point in time as more worker reports are coming, and also for assessing the confidence of the system about the correct answer. And we also have vote models for predicting the future execution, for saying, if I hire another worker, what that worker would tell me. And these next vote models help us to say, predict the future and say, what am I expecting to happen in the future, and with that improvement in the future be enough to compensate for my additional costs in the future. So it will enable us to make that kind of an analysis. And we have a decision-theoretic planner on top of these predictive models that makes these hiring decisions in a way that optimizes the final utility of the system. We are performing the study of CrowdSynth ideas on a well-known crowdsourcing platform called Galaxy Zoo. Galaxy Zoo is a project that is introduced by the Zoo Universe team. Zoo Universe team has been phenomenal for introducing a number of very influential citizen science applications to the web, and they have actually energize a large community of citizen scientists. What citizen scientists, what we mean is that regular people in the world, we just have internet connections, and they want to make a difference in science, and they want to contribute to the science. So they have these platforms for engaging the regular people in the world to scientific research. So this Galaxy Zoo system is one of their most successful applications. The goal of Galaxy Zoo is asking regular people in the world, these citizen scientists, about the type of galaxies. So this system, when a citizen scientist comes to the platform, the Galaxy Zoo system shows an image of a galaxy. And there are millions of these galaxies, but there are not enough experts in the world to classify all of these galaxies. So the citizen scientist looks at this picture and says, I think the correct classification of this galaxy is elliptical or spiral or merger. And the idea is that if we can ask enough people about these classifications, we can classify them correctly. And actually, they have experiments showing that the citizen scientist classification matched the expert opinion. So that it has been very successful. And since the launch of the Galaxy Zoo project, hundreds of thousands of people have contributed to Galaxy Zoo. They have successfully classified millions of galaxies. And this resulted in discovering new galaxy types and new astronomical objects. And this led to more than 12 research papers, which increases our knowledge about how the galaxies evolve in time. So we want to thank the Galaxy Zoo team for giving access to this beautiful data set to us for our studies. In this data set, there are more than 34 million worker votes collected for nearly 900,000 galaxies from 100,000 unique workers. So the first step we take is generating a set of features that are describing these consensus tasks. So the first set of features we have is task features. These task features are the results of automated task analysis, which uses computer vision algorithms to look at these Galaxy Zoo images and gives us different features representing the images. For example, how much noise these images have, or what is the radius of a galaxy we see in the image. And these features are coming from the Sloan Digital Sky server, and we have 453 visual features like this. This represents the automated task analysis component. In addition to this, we defined a set of vote features that guess the sequence of votes collected for a task so far, and then represents how these votes look like. What is the distribution? Number of votes for each class, the entropy of the distribution, the mode class, and many others. And we also defined a set of worker features. We said, based on the historical data that we have, what is the usual time these workers spent for each task, how much experience they have, what has been their accuracy for different kind of tasks. And we also define some vote worker features which uses vote features in addition to the worker features to generate better descriptions. So now that we know how we are doing the feature generation, I will talk about building the predictive models. In consensus tasks, there are a number of different uncertainties. For example, the system is always uncertain about what the correct answer is. And also, it is uncertain about what the next worker would say if we hire an additional one. So we are building these predictive models for representing these uncertainties. Answer models predict the correct answer, and vote models predict the next vote. This figure on the top represents one particular model we built for predicting the answer and the next vote. And as you can see, this model can bring these different features together to make the predictions. And we use supervised learning with Bayesian model selection to train these models. For predicting the correct answer, we took two general approaches. The first one is building a generative model that makes an inference based on a prior answer model that is just using the automated task analysis features, and a vote model which predicts the next vote based on the correct answer, task features, and vote features. And then we implemented two very well-known generative approaches, a naive Bayesian model which makes an independence assumption about the votes coming for a task, and an iterative Bayes update model which does not make this assumption. And then we also tried a discriminative approach which learns a direct model from all the features available for a task. In this graph, we can see the different accuracies of these models when the number of votes are increasing from 0 to 60. So one important lesson from this, as the number of votes increases, we can see a benefit for using a discriminative approach because the votes are coming together in synergic ways and the discriminative model is able to represent this. But in addition to this, for these consensus tasks, these tasks are really difficult. We may need a very large number of worker reports to be able to predict the correct answer accurately. And in this figure, we can see two discriminative models. One trained for the case where we have few number of votes, and the second one trained when there are a large number of votes available. As you can see, when few number of votes are available, the task features are really playing an important role in predicting the answer and the vote. But as number of votes increases, the vote features become the big predictors for the correct answer. So now that I've described how these answer and vote models are trained. Now I want to talk about how we will make decisions by using these predictive models. So the goal of the decision-making component is optimizing hiring decisions to maximize expected utility for solving these consensus tasks. And here we are defining the utility as the final accuracy of the answers produced by the system minus the payment we are giving to workers. So we don't want to hire a lot of workers because they are costly. We can't hire infinitely many people, but at the same time, we want to get to a good accuracy, and the system needs to do a good trade-off for different cost values. And we are modeling consensus tasks as a finite horizon Markov decision process with partial observability. The state here includes task features and votes. At each step, the system keeps a belief about what the correct answer is. And here, the system has two high-level actions. The first action is hiring a random worker and continue the task. The second one is not to hire a worker and terminating the task. The reward for taking a hiring action depends on the cost of a worker, and the reward for not hiring any more workers depends on the confidence of the system on answer prediction. And the stochastic transitions of the model is determined by the next vote models. So as you can see here, the predictive models become inputs to our decision-theoretic planner. And the decision-theoretic planner makes a decision about whether to hire new workers or not. And this decision about which action to take is guided through a value of information analysis. So for each state, the system decides what is my value for taking action H versus action not H, and I should take the action which provides more expected value. However, just using regular MDP or POMDP approaches for solving these tasks is not possible, because the horizon of these consensus tasks can be very large, and we know that when there's partial observability, the complexity of solving these models grows exponentially with the horizon. Which makes the exact solution approaches infeasible. For some Galaxy Zoo tasks, we have up to 90 votes, so we need to do a horizon of 90, which is not feasible. So what is our solution for solving these tasks efficiently? The solution is understanding the spatial structure, because consensus tasks have a spatial structure. There are two high-level actions, hire a worker or not hire a worker. The task terminates when not H action is taken. Each higher action adds new evidence, and answer predictions are most accurate at the horizon when all votes are collected. So by looking at this spatial structure, we designed a new Monte Carlo planning algorithm that can solve consensus tasks efficiently. So what this algorithm does, it starts from a state Si, the current state of a consensus task, and it generates samples. Each sample represents one future possible execution of the system if the system continues to hire as many workers as possible until reaching the horizon. So starting from the state Si, we say, OK, I'm hiring a worker. Let's sample what that worker would say. Maybe that worker would say elliptical or spiral. Update state, take another hire action, sample another worker vote, update the state, and continue this until reaching the horizon. At the horizon, we have a lot of evidence about the task. At that point, from the belief at that state, we can sample a correct answer, which is A bar. And then now we will use the sampled correct answer to backpropagate and then evaluate what the values of previous states are for terminating at any point. So backpropagate this A bar to the state St and say, if we terminated at that state, if we took action not H, what that state would say as the correct answer, does that agree with the sampled correct answer? If it agrees, here's a good reward for you. If it doesn't agree, there's a bad reward for you. And we do this for all states encountered on the sample. And at the end, we can assign some utility to these different states we've seen on the sample. And then later, after we generate many samples like this, we can bring these samples together in a search tree, in a partial search tree like this. Here, the branches represent the stochastic votes that we can get from workers. And starting from the bottom of the tree, we can evaluate for each state on this partial search tree what the value is for hiring workers or not hiring any workers, and make decisions like this. So what are the properties of this algorithm? It is an anytime algorithm. With each sample, we can explore states at different depths, which is a good property when the horizon is so long. And a single sample can evaluate values for multiple action sequences. So by using these properties, we can solve consensus tasks efficiently. Now I will show you results from an empirical evaluation we did with the Galaxy Zoo data. we compare CrowdSynth to two baselines, no hire baseline, which hires no workers, just uses the automated task analysis, hire all baseline, which is the original Galaxy Zoo system. And we tried different CrowdSynth variations, a limited look-ahead approach, which looks 16 steps look ahead, UCT, which is an upper confidence bound Monte Carlo algorithm, Monte Carlo to research algorithm, and our novel sampling-based algorithm. And in this graph, you can see the utility of the system when the cost of hiring a worker, cost for a label, decreases from 1 to 0.01 cents. And as you can see here, when the cost of a worker is not very high, our algorithm and CrowdSynth can do much better than all the baselines and all the other Monte Carlo planning algorithms. And why we see this? Because our system can successfully trade off the expected benefit of a worker with the cost. As you can see here, the blue line is the accuracy of CrowdSynth. The red bars represent the percentage of votes collected. And as you can see, when the cost is really high, the system does not hire many workers, but it can still increase the accuracy upon the baseline. And as the cost decreases, it increases the number of workers it hires, and gradually the accuracy increases. And finally, at the end, when the cost is really low, CrowdSynth can reach the maximum accuracy of the original system by only hiring 47% of the workers. We did a similar analysis when there's no cost for a worker, but there's a fixed budget, and we showed that CrowdSynth can do much better than other baselines. So I know I'm out of time, so I will just conclude with a future work or a current work slide. What are the things we are working on right now? This version of CrowdSynth works if there's a large set of historical data. We are interested in how we can use the same ideas when such a data set is not available. So we are interested in a design of a system that can learn and act simultaneously. We want to go beyond consensus tasks. For example, the picture on the right is another example from a Zoo Universe platform where it's no longer a consensus task, it's a discovery task. And we are interested in other prediction problems like predicting engagement of workers. And we have an ongoing collaboration with the Zoo Universe team. They are very interested in trying these ideas in their platform. So we want to really see these ideas come true in their systems. So thank you very much. And I'd like to have your questions.
It sounds like your system really is beneficial if the task is hard. So you really need multiple judgments done, and also it assumes sort of one judgment at a time. Like it collected three workers, as we call them, like or three judgments, and then decides whether to go for the fourth one or for the fifth one. In practice, you usually cannot really get only one because you have the problem with bots and stuff that you have to keep filtering. So you have to usually get them in batches.
How do you need to get them in batches?
In batches because you have to keep looking at you have to keep filtering the bots. I guess you can change it.
So,
not necessarily. The question is, what would change if we either have like very small budget, like we really cannot go past 5 labels per thing, and also what would change if we have to we cannot request 1 label at a time. We would have to request like 5 labels or 3 labels at a time.
So the ideas would be pretty much the same, and you can hire 50, but you can hire 5. Your decision-making problem will get much simpler because now you just need to think about 5 steps ahead at most. So you don't have many of the challenges we've seen in the problem. So actually the task becomes simpler when you can hire at most 5 workers. And what we've seen here, even for the Galaxy Zoo tasks, there were times where the system was confident enough to say that I'm done after hiring 1 worker, because the automated task analysis was already confident that it was elliptical. The first worker system hired said it's elliptical, and the system said, yes, with these costs, I don't think I can improve much better by paying more workers. I'm just stopping now after 1 worker. So even when the number of workers you need to hire is not that large, you can still generate benefits by using an approach like this. And coming back to the question about batches, such a system will be more beneficial when you can actually dynamically adjust what you want to do after each vote, because then you have more freedom about how much granularity of workers you want to hire. But the same idea would still work. Instead of hiring one worker, you want to hire couples of them. That would still work. But at the end, you may not really juice all the benefits you like to get out of the system just because your decisions are not that, granular. Yes. Yes.
So it looks like your action space you're looking at is hire or not hire, and that's fine, but in practice, often I have a fixed budget and I want to do the best I can. And have you looked at, instead trying to determine which tasks to give, more of a crowdsourcing active learning type of approach? It seems like similar techniques can work, but that didn't seem to be in scope at all here.
Here, because of the limitations of the data set and the Galaxy Zoo platform, we can't really target individual workers. This is why we've performed our simulations like this. But in separate simulations that I haven't presented today, we built next vote models that were personalized. So we were actually predicting what this particular worker would say for this galaxy, and then customized our decision-making model by also making decisions about which worker should I hire if I can hire between these 30. And you can actually see benefits in doing that.
That's still about who to hire, which is closer. It's not, what you could do is say, it's not about what example, what tasks, what actions, what questions do I give?
That is like the analog problem, but looking at from the task. So the same ideas would be applicable for doing that kind of an analysis too.
Okay, let's take the speaker on the top.